Hi, my name is Bill Kinney, and this is part 2 of a series that I'm making on geometrically interpreting the chain rule in multivariable calculus. If you haven't watched the first video, you definitely would want to make sure you do that because I'm going to go through the content of that first video very quickly. And it's confusing. There are lots of ideas going on here, lots of symbols. First of all, what's the situation we're considering? We're considering a function that's made up of two functions being composed together, plugging one function into the other. In this case, the outer function f is labeled f, and the inner function is labeled capital Phi. We're plugging capital Phi into f, as you see down here, which ultimately can be thought of in terms of the coordinate functions of capital Phi, which I'm calling little phi and little psi. In that kind of situation, if f and capital Phi are differentiable, you can write down the derivative of z with respect to u and with respect to v in these two ways that you see here. Keep in mind here z initially depends on x and y because of the function f. Then x and y individually depend on u and v because of the phi function. To be even more specific, we can now consider this situation where the phi function is a very special kind of function. It's a transformation that converts polar coordinates to rectangular coordinates. So given a point r theta, you can convert it to a point xy with this equation here. You can also think about each of the coordinates individually with these two equations. And we looked first of all at what the chain rule says in this situation. Now r and theta are going to play the role of u and v. Here are the most general formulas there and there, with again r and theta playing the role of u and v. But then for this specific transformation, I differentiated these functions that you see here with respect to r and theta and plug them in. For example, the derivative of x with respect to r, looking back up at this formula again, was cosine theta. That's what I plugged in here, etc. I found the derivative of y with respect to r, plugged it in there. Down here I found the derivative of x with respect to theta, plugged it in there, and the derivative of y with respect to theta, and plugged it in here. And then the final thing that I did in this video, the last video, was that I noted that for this particular example, these partial derivatives come out kind of nicely. Well, they can always be thought of as dot products, but they come out as kind of nice dot products. The gradient of f, which will always be there, dotted in the first case with a vector cosine theta comma sine theta. That'll be what you get when you differentiate z with respect to r. In the second case, when we're differentiating z with respect to theta, we can think of it as the gradient of f dotted with this special vector there, negative r sine theta comma r cosine theta. Let me also remark here in this video that this dot product can be thought of, if you like, as the following dot product. This vector here, cosine theta sine theta, is a unit vector. Its length is 1, and in fact, because of these conversion equations that are up here, if you solve those equations for cosine theta and sine theta, you'll get x over r and y over r. So in fact, that vector can be thought of as this. In other words, the position vector of the point that we're at divided by the length of that position vector r, the polar coordinate of the point r, is what we divide by here. It is a unit vector, is what we're dotting them with here. And with the second one, this thing is not a unit vector because r is not necessarily 1. But we can think of this in terms of x and y as well. In fact, negative r sine theta is the same as negative y, and r cosine theta is the same as x. All right, what's all this going to mean for this particular function that I picked? F of xy equals x squared minus y squared. Well, we need to find the gradient of that function. The derivative of f of xy with respect to x is 2x, and the derivative with respect to y is negative 2y. So I can put a 2x comma negative 2y in here. And what that's going to then mean, if I copy and paste these down, is that for the partial derivative with respect to r, I could ultimately write this by doing those dot products as 2, well, let's write it like this, 2 x squared minus 2y squared over r, which would be the same as 2x squared minus 2y squared over x squared, square root of x squared plus y squared. That's at the point labeled xy. You can also convert this in terms of r and theta, and you would probably expect that you would do such a thing. Maybe I'll go back up to thinking of it up here. The partial of z with respect to x is 2x, the partial of z with respect to y is negative 2y, and if I replace x with r cos theta and replace y with r sine theta, we ultimately see that this can also be written as, let's see, x negative r squared cos theta. Oops, I'm looking at the wrong thing. I need to look up here for that one. So it's actually going to be an r cos squared theta plus r, excuse me, minus, forgetting a 2 here as well, 2r cos squared theta minus 2r sine squared theta. Again, what I did there was I was looking up here, and I was replacing dz dx with 2x, and then replacing that x with r cos theta. So I got a 2, and I got an r, and then I got another cos theta that needed to be put on there. And then I looked at this one, replace the dz dy with negative 2y, and then replace the y with r sine theta. So I get a negative 2r sine squared theta here. And then the other one, put down here, I guess it's not in red here, replace dz dx with 2x, and then replace x with r cos theta. You're going to get a minus 2 r, let's see, r squared cos theta sine theta. And then do it with the other one, the dz dy. You're going to get something that does turn out actually to be the same. So in the end, we get negative 4r squared cosine theta sine theta. How can this be checked? It's actually most simple to check it by differentiating this function with respect to r and theta individually. I'll just write that out. If you do, I'll let you pause the video and check this. If you look at this expression especially, if you differentiate that with respect to r, think about it, treat theta as a constant, you are going to get this expression right there. And if you differentiate it with respect to theta, keeping r as a constant, initially you'll get this, but then it can be simplified to that. So you do get the same thing either way, so that's checking it. That looks like it's got to be the main goal of this particular video, since I'm low on time as far as a 10-minute time limit. In the next video, we're going to look at how this can be interpreted geometrically, and this is probably the most important part of it. All this code is going to lead us to interpreting it geometrically. I will enter the code here in this video, and we'll take a look at what it looks like here. Take a look at how these axes are labeled. One's labeled r theta, one's labeled xy. I've got this point that I can actually move around with my cursor, and a corresponding point over here moves around with some vectors shown. And in both cases, you've got a contour plot, contour map of some functions in the background. I will come back to this in the next video, but you might spend a little time seeing if you can figure out what in the world this is all about. I also have some sliders up here. change A here, and you can see something happening on the right there and on the left. Change B, you see something else happening. There we go. So I would encourage you to see if you can figure out, it's going to be a challenge, but see if you can figure out what in the world this picture is all about, and that'll be the main focus of our next video.